All semester we have been marveling at the various forms of magic that C++ provides that make programming so convenient. One of the very first forms of magic that we saw was the magic of the vector in C++, this strange array-like object that can grow and shrink as needed and doesn't suffer from any of the same drawbacks that C-style arrays do. And so I think a refreshing change from C. And while it's great that C++ is so powerful and provides so many features that it does indeed look like there is magic in the language, there isn't. There is, unfortunately, still no such thing as magic. And while we can celebrate the fact that it almost feels like magic to program with things like vectors, we shouldn't get fooled and end up believing in magic. So although it's still great to use vectors in our code, we should see at least once exactly what is going on behind the scenes and convince ourselves that, yeah, it's sort of nice to be able to use it like it's magic, as long as we understand that it really isn't magic. And so in this next sequence of videos, I am going to write a pretty convincing doppelganger of the vector class in the standard library. Now, it turns out, though, there is a bit of magic happening in the vector class in the standard library that's even above the level of the course. Most of that involves features that we are not going to use in this course, things that we haven't used, functions, member functions of the vector that we've never actually seen in the course. But there are a few quirks of the way that classes are constructed and destroyed that the vector does have to take into account that we aren't. So what I'm going to create is a little bit simplified from the real std vector type, but I think as far as we're concerned, as far as we've been using the vector, it should illustrate that what's really going on behind the scenes actually isn't magic. I'm going to split this over a few videos for a lot of reasons, one of which is there's a lot of work to be done. So what I want in this video is to create a type called int vector. So one thing we're going to put off until quite a bit later is the discussion of how do I use the angle brackets? How can I create a vector that can store any element type? But I think in this next few videos where I create the int vector type, you can see, once we get to that point, you'll be able to see how we could work backwards and parameterize our vector type to take any element type we want. So I want this type called int vector, and we can see here I can use push back on the type, and then I can print the vector out, and the function that prints it out just uses indices for now. We're going to develop it later so that I can use a for each loop. I want even to take advantage of that. I would like to be able to write an object that provides all of the same convenience that the real vector class does. And we know that C++ holds nothing back. All of the stuff the language designers were allowed to use, we are allowed to use too. I can write my own objects that I can iterate over with for each loops. But for now, we're just going to iterate over it with indices. I have push back. A vector does not normally provide push front, so we will not either. I'm going to provide this square bracket operator with all of the same quirks as the real vector. So for example, there's no range checking on the square bracket operator I am going to define. I'm going to define .at, just like a vector. I'm going to add the pop back function, which vectors do have, although we have not really been using it very much. And I'm going to do a bunch of other stuff too. We're going to begin talking in the next couple of videos about stuff like what happens if our vector is constant. We know that we often pass vector objects by constant reference. What happens if I want to make copies of vectors? So what do we do with our copy constructors and copy assignment operators? And then finally, how do I make vectors work with for each loops? And it turns out that that is coupled to the question of how do I make iterators work over a type of my own creation. For today, though, what I want to talk about is how to create a basic vector class that stores only integers and internally stores its elements using a C-style array. For today's video, for this one video, our storage array is going to always have capacity 10. So this vector will never be able to grow beyond 10 elements. Now, in a future video, we'll talk about how to make the underlying storage resize, how to actually allow the vector to grow and shrink dynamically. For now, because we have to introduce one new piece of notation that we're never going to need again after this video, that allows us to use C-style arrays, for now we're not going to allow the array to be resizable. So in this video, I want these features. I want a constructor. For now, we will just write a default constructor to create an empty vector. Our constructor will make an underlying storage array that's encapsulated inside the class that has capacity 10. The vector will also keep track of its size. So although the underlying array might have capacity 10, the vector might only have 3 elements, because we know the vector will dynamically grow and shrink as elements are added and removed. The way that we conceptualize this internally, the way we implement that abstraction, is by making an array of some obvious size, like 10, and then just representing to the outside world that only a certain amount of elements are present by only using a certain amount of the array. I'm also going to have a destructor. I need this because I'm going to have to use dynamic memory allocation for my storage array. That means I have to use the delete operator in the destructor. I'm going to add square brackets, the square bracket operator, which is an operator we have not seen yet, but by now we know that we can define operators on classes. I'm going to define a member function .at, and I'm going to define member functions pushback, popback, and size. For now, because in this video our vector will not dynamically resize, it is possible that I can call pushback so much that the vector's underlying storage array becomes full. If that happens for this video only until we get to part 3, we'll just throw an exception and say, sorry, the vector is full. Okay, so what do I have so far? Well, besides what I already showed off in main, I have this. Internally, the vector will be stored, the contents of the vector will be stored in a C-style array. I will keep track of how big that array is with this variable called capacity, and we'll set that to 10 in this video. The C-style array will be referred to by this pointer here, this C-style pointer. Now, the way I'm going to use the array here is the same way I would have used the C-style array in 111. We're never going to need C-style arrays after this sequence of videos because we will have proven that we can successfully wrap them up in a vector object. That is why I'm not going to make too much of a big deal about the array notation I'm going to use here. The thing you have to remember from 111, though, is that remember we can use int star, so pointer to int, as a way of pointing to the first element of an array. And if we have something of type int star, we can index it with square brackets like we index any array. That's the same syntax we would use in C for this. I'm going to store the size of the storage array. This is setting me up in a future video to have the array change size, or appear to change size. And then I'm going to store the actual number of elements in the vector, keeping in mind that my storage array might have more elements than my vector actually contains. So I have to keep these two pieces of information separate. Now, for the sake of keeping things moving here, I am actually going to try and plow through all of these function implementations at once. Generally, when you have to implement a data structure, you have to put up with a certain amount of this. As we know, good programming practice says that we should try and test our code as often as possible. So I should write as little code as possible and then compile, run, and test it. And I should do that iteratively. In this video, because that can be a little bit tedious to watch, I will move a little bit faster than I would normally go if I were developing myself. And that's mostly to try and keep the video well paced. But it's also because when you implement a data structure with multiple features, you do occasionally have to write more than one feature at a time because you can't test one until you've written more than one. So an example being, I can't test out pushback likely until I've written .at or square brackets, because how do I test that the elements are there until I can retrieve them somehow? Similarly, I can't really test pushback until I have a constructor. And I can't reasonably test that the constructor is working until I have some way of adding elements to my vector. There are workarounds you could use for this and that I would use for this in practice. So you could use unit testing. You could add some phony elements to your vector before you've written pushback as a way of validating that your storage array works. Those are all valid options. On assignments, you might want to try that. For the video, because I want to focus on the operations themselves, I'm going to be a little bit cavalier. And that's why I'm giving this disclaimer. What I'm doing moves a little bit faster than actual development in practice. That is because watching me for 3 hours on a video get the vector right by trial and error, by constantly testing and writing my own test cases, would not prove to be a very compelling watch, and I'm fully aware that the video is probably not already a compelling watch. So I'm going to move a bit faster than I normally would. Okay, so I'm just going to go through and I'm going to begin by mocking up the functions that I need. So I'm going to write basically a hollow constructor and destructor and square bracket operator and then go through and fill them in. So here's my default constructor, int vector, and I'm just going to leave that blank. And then I'll write my destructor, and I'll leave that blank as well, just to have a signature for all the functions that I need. I'm going to write my square bracket operator. So the square bracket operator, what I want to do is I want to assign ints to the result of the square bracket operator. So each element of my vector is an int. I want to be able to assign to what comes out of the square bracket operator. I also want, of course, the result of the square brackets to be one of the elements of my vector. But because I want to use them in assignment statements, I should observe that I want the square bracket operator to return a reference. Because we know that unless the function or operator returns a reference, you can't just assign to what it sends back. So what I'm going to do is assume, therefore, that my square bracket operator should return something of type int reference. And it'll be operator square brackets. And the way you write the square bracket operator is you write it with the usual function style notation, but curiously, the name of the operator is square brackets. Where you put the thing that goes in the square brackets is just given as a normal argument like any other operator. So in this case, it'll be the index that was provided. So when I write operator square brackets, I just use empty square brackets in the name of the operator. Similarly, I want to write my .at function, so it'll look like this. I'm going to use unsigned ints for my indices. There we go. I then need pushback and popback, and as per tradition, those return void. So pushback takes a new element, so we'll do int element. And in this vector, it is storing signed ints, so not unsigned. I use unsigned ints for indices, but a regular int for the elements. Okay, and then I've got popback. So popback doesn't return anything. It doesn't take any arguments. It just deletes the last element of the vector. And then finally, I want .size. So I'll return unsigned int size. All right, and I might already want to take a look at whether I can make anything constant. I think I can make this function constant, but for now I'm going to leave that out. We'll talk about that in part 2. There will be a bit of a snarl with what functions we can make constant. That's why I want that to be a separate video. Okay, so I have signatures for all the functions that I need. They're all in the public section of the class. I'm going to make this a bit smaller while we write them. And now I want to go through and begin filling stuff in. Okay, so here in my default constructor, I want to make a storage array with capacity 10. Now, how to create C-style arrays with dynamic allocation is something we have not seen. I'm going to use it in this video, and although I know it's coming up out of nowhere, we're never going to need it again in this course. That's why I'm justified in doing that. And then set the vector size to be 0. So before I do that, I'm going to initialize the members before I set up the storage array. I'm actually going to set the storage array initially to be a null pointer. Okay, and then I guess I will also set up the vector size. This is meant to be the real size of the vector, and this number will be the number of available spaces in my array. So normally we should initialize elements in the same, initialize the members of the class in the order in which they appear. So vector size first, then capacity, which will end up being 10, and then my storage array will be a null pointer. I could also initialize the storage array directly to be a new array, but I'm going to use the notation here to show off what we do to dynamically allocate an array. I want my storage array to be an integer array, in this case of size 10. So new int size 10. I could also do this because we know that the member capacity is equal to 10. I think this is a bit cleaner because we always want this variable capacity to equal the size of our storage array. So it makes sense to deliberately use capacity when we're creating the array. So the new operator has a special case where I provide square brackets where it doesn't just create one instance of the thing I want, in this case an int, it creates a whole C-style array of them. When I want to delete that object, I have to use this special delete operator, delete with square brackets. We don't need to worry in this course why there are two different versions of the delete operator. So in a nutshell, what's going on here is when I deallocate a big array of objects, it requires a different type of work than when I deallocate a single object. Because when I deallocate an array, I have to go through every element of the array and destruct it. And therefore, the language has to have some way of knowing whether I'm deallocating one thing or an array of things. And so in this case, I use this special delete operator. Now, that's weird. Don't worry about it. We're never going to see the delete array operator again. We might see delete again, but not this special array version of it. Now, what about the square bracket operator? So it's going to return an int reference, a reference to one of the elements of this vector. And recall that just like a real vector, the square bracket operator of my vector does not need to do any range checking. So I'm going to make no effort to validate that the index that was provided actually is valid. Instead, I'm simply going to go into my storage array and grab that index, being fully mindful that obviously if the index is invalid, I'm going to walk past the end of my storage array. Recall from 111, that would be a very bad idea. But we know from the real vector in the standard library, that is actually the expected behavior of the square bracket operator. I'm going to take a little detour and write the size function now. So let's see, what is the size of the vector? Well, we have this member variable, vector size, that is the number of elements in the vector. So I'm going to return that. And hopefully that's not too big of a deal. So I just have the size on hand, so I return it. It really isn't any of the outside world's business what the underlying capacity is, because the outside world doesn't care. It should just know how many elements are really present. Now, the real vector in the standard library does give you a way of knowing this. It actually gives you a way of setting it yourself if you want to. We're not going to worry about it because we like this idea that the vector presents an abstraction. What about the regular .at function? Well, we know that the .at function is supposed to have range checking. So I'm going to ask here, if the index is greater than or equal to the size of the vector, well, the last valid index of the vector should be the vector size minus 1. So if the index you provide to .at is greater than or equal to vector size, we've got a problem. And so here, we will throw that out of range exception we've been getting all semester long when we call .at on an invalid index. So I'll say invalid index. There we go. And then otherwise dot add is the same as the square bracket, so I just return storage at that position. Of course, when I get to line 41, I can be assured that it's a valid index, that I actually am allowed to go into the array at that position. All right, what's next? So push back. Let's see. So to add a new element to my vector, I mean, I can sketch this out, but conceptually, I've got a vector. It's got some stuff in it, so here's some elements. And right now, the size of the vector would be 3. So my size here equals 3. But the capacity could be larger. So my capacity might be larger than 3. Nobody outside the vector class should know anything about that. It's none of their business. I pretend as if I am actually just an array of 3 things. My vector impersonates an array of 3 things, even though secretly, deep down, it might be using an underlying array that is bigger. And so what I'm going to do here is, with my push back function, all I want to do is if you give me a new element, I add it to one of these extra spaces at the end, and then I just correct my size variable to say 4. Which gives the impression from outside that the vector grew. So that's ultimately what I want to do. So what I do is I go looking, let's rewind a bit. I go looking for what is the first index, or what's the first empty index. So currently my vector has size 3, and notice how that means the first blank index after the contents of the vector is index 3. In general, if my size has a particular value, that is also going to be the index of the first blank space. So I'm going to store into my storage array, storage at index vector size, that's the current size of the vector, I'm going to just store that new element. So conceptually, the size is currently 3, store the new element into index 3. And then after that, I'll just increment the vector size to reflect that there is now one more element. And so now the size encompasses everything up to here, and the size is 4. Connoisseurs will note there is a clever way of doing this all in one line. You go right ahead and do that in your code. I'm going to do 2 lines because I want people to learn something from this. But basically, I just add the element to my storage array, and then I increment my vector size. And then finally, pop back. So actually, it's interesting here. The pop back function, what does it really do? Well, it's supposed to remove an element. Now, if we were storing elements of some class type with a destructor, there'd be a little bit more work involved here. But what does it really mean to remove an integer? Well, actually, I have this array of size 4 here, this vector of size 4. When the pop back function is over, the vector is supposed to end after the 17, as if this element had been deleted. But I don't really have to delete it. I just have to pretend it's no longer there. Somebody looking in from outside, if the size is suddenly 3, I think they'll be convinced that I did delete the element, because the int element doesn't have a destructor. There's no other way of knowing whether it's secretly still there. So actually, in this case, all I have to do is decrement my vector size. And then from the point of view of the outside world, that gives the impression that the element indeed was deleted. More work would be needed here if you were storing elements of something of a type other than int or float, a type that had a destructor. But in our case, we're taking small steps. All we're worrying about here is type int. Now, before I go further, I should add a bit of protection to this. So the first thing is, right now, the capacity has been capped at 10. So if the vector size, when I try and add a new element and push back, if the vector size is equal to the capacity, we have a problem. So normally, if the vector size equaled the capacity, so if my underlying array only has 4 positions, and my vector has size 4, so for example, if I'm in this situation, size is 4, my underlying array is full. If I do push back, normally that is where the vector would do one of these clever operations that resizes the underlying array. It resizes it by making a new array and copying the elements in. We're not ready for that yet. We're going to do that in part 3. So for now, if we reach that case, we're out of luck. And so I'm just going to throw a runtime, I'm going to throw a logic error. It's an exception we haven't seen before. But I'm going to say, sorry, this vector doesn't support resizing, so you can't add another element. And I'm using logic error because I'm indicating this is actually sort of a programming error. You've done something that the program simply can't permit. It's not really a runtime error because this is a situation you should have seen coming. And then down in pop back, I'm going to do something similar. Although we're going to get rid of this exception in part 3. The one I'm going to add to pop back, I think we're going to keep, which is if the vector size is 0, so if the vector is currently empty, I can't reasonably subtract an element from it. I can't delete something. If I try to decrement the vector size, I'm going to be in real trouble. So here I'm going to throw another logic error, which is that you really should not be, actually I think this might be a better situation for a runtime error. Somebody should not be using the vector this way. Cannot delete from an empty vector. All right, because I do not want to address the situation where my size is 0 and I try and decrement it. And then I skim over what I have. So it looks as if I have the basic idea here. I've got the vector, I'm creating a storage array, I'm deleting the storage array, so I'm fulfilling my obligations to ensure that everything I allocate gets deallocated. I've got square brackets, I've got my .at function. I suppose I should just try compiling it and hope for the best. There we go into my window with my terminal, press enter and see what happens. It does compile, and so we'll go down to main, take a look at what main contains, and then hold our breath. Actually, I just resaved the file. We'll try compiling again. There we go. So what I should see when I'm done, if I run main, is I try and, in my print vector function, I take the vector by reference. So there's no need yet to talk about copies. I print out the size, and then I iterate over the elements with indices up to size -1, and I just use .at to print them out. That means if print vector works, there's, I think, a good case to be made that .size and .at work correctly. And of course, push back will have to work correctly for print vector to print anything meaningful. I should expect, therefore, to see that in part A of main, I get the vector 6, 10, 17, 187, which has size 4, and I get the vector 111, 116, 445, which has size 3. In part B, I modify one of the elements of V1 to be 999, so element in index 2 would be this element. The 17 should change to 999. And then I modify the element at index 3 to be -1, so that would be this element of V1. And then I remove the last element of V2, so V2 should then have size 2, and then I print both of them out. So we'll take a look. Whoops, I didn't name the program correctly. There we go. Okay, so after part A, I print out the vectors 6, 10, 17, 187, and that looks good. And it's got size 4 as expected. And then I print out the vector V2. It has size 3. In part B, I modify V1, where index 2 contains 999, also looks good. Index 3 contains -1, that looks good. And vector V2, after the pop back operation, its size has indeed decreased to 2. And recall, internally, inside the vector, encapsulated inside the vector, we know that the pop back operation is actually doing a sort of dirty trick. It's not really deleting anything. It's just pretending that the vector is now a little bit shorter. But because of encapsulation, we have no way of knowing that. When we iterate over it, when we ask it for its size, we only see a vector of 2 elements. And that's one benefit. We don't care using the vector what it's doing. We just care that when I use pop back, the element is gone. So over the next few videos, I want to make a few improvements to this. One of them, the first one, is I want to be able to pass my vectors by constant reference. And I suppose I could show off what happens if I try doing that here. I'll try compiling again. And it is not happy. And we know already that there is some nuance to making certain functions constant. So we want to do that first. Then I would like my vector to function just like the real vector as a resizable array. I would like it to be the case that I can run pushback as many times as I want, and the vector is able to just absorb those elements. It never fills up. The one I've constructed here will fill up. Just as a transitional measure, this vector only ever can store 10 elements. That's it. Obviously, in part 3, I will want to remedy that. I want to achieve the real abstraction of the vector as an arbitrary sequence. And then I want to talk about things like copy operations. So I want to talk about why I need a non-trivial copy constructor for my vector. And eventually, I want to design it so my vector supports iterators, which, as it turns out, will allow me to run for each loops over my vectors.